How would you answer this question? Like, what's the process of answering this question? Wait, partner. Okay, that's good enough. What? Anyone willing to tell me? Okay, you might look and see if it's one you didn't memorize. It's not going to be that. They're all going to be weak acids. All of them will be. Yeah. Nope.
We look at the K.
It's going to give you the KAs.
So whichever one
The smallest value. That's what you're looking for. And remember, a -10 exponent. And like a -3, which was the smaller number? This one. Some people, for some reason, get it backwards once in a while. Like, oh, that's a 10, that's a 3. Don't get that wrong. Okay, next. Consider the following chemical reaction at equilibrium in a particular experiment. The concentration of those. We've done this, but this is on last test. This exact problem. I'm not going to worry about that. Which one of these is not a strong acid? Well, never mind. These are the strong ones. What I did last year is I cut out all the options. So, like, don't choose any ones there. It'll be A, B, C, D. But here are your strong acids. By March, right? It's March. This should be committed to memory. So it'd be 3 of these, and then like HF or something. They really like HF because it seems like, hey, it's in family 7. Everything else is, well, it's not. HF is a weak acid, right? So you say no. You with me? All right. Would this problem give you 4 KAs to choose from? Why? So, you know, it's okay if you don't. You want to know why? Yeah? Good. Because strong acids, we don't do their KAs because they're different. We would divide by C. All right. So, good. All right. The magnitude of KW indicates that, well, this is a weird question. I don't even know what the options are. It could be the solubility of an acid in a water, something like that, most likely.
What is KW?
It is for with the equilibrium for water. KW is equal to the concentration of H plus times the concentration of OH minus. So it's just how these break apart. By the way, each one of them is 1 times 10 to the -7. We did. This is on the negative. We could use one. Just one of these to find out the other one based on that. All right. There's no options here, but describe of the following equilibrium, only blank will shift to the left in response to a decrease in volume. So how would I write out these options? The thing says it has to go left. The decrease in volume is their way of saying what? Okay, it's an increase in pressure, right? So what should we be looking for here? You want to go left and increase the pressure?
So less moles.
All right, so a small amount of moles versus large amount. It's going to go on the smaller side. This is last chapter. Okay, do you know how to do this? pH, this is just simple math, equals the negative log of H plus. So pH would be equal to the negative log of 0.0025. Compare that. Okay. This would be just 10 raised to the negative 4.282. You're going to be able to go both directions, from concentration to pH and from pH to concentration. They give you the temperature because this is temperature dependent. Now, is it something I'm gonna plug in? No. But the concentration of something is absolutely dependent on the temperature of the solution. So all these problems on stuff like this, it would give you the temperature, even though it's mostly useless. At equilibrium, that's from chapter 15, but how could you finish that sentence? Use the word rates. Tell your partner, at equilibrium, something to do with rates. All right, yeah, the forward and reverse rates are the same. There's the answer, but here we go. The conjugate base of HSO4 minus is. So that would mean this is an acid, right? Now this looks kind of weird because it's usually H2SO4, right? That's okay. When H2SO4 breaks apart, the first thing it does is it kicks one of the H's out, and then what's left? HSO4, and it's going to go to H plus SO4 minus 2. All right, so going this direction, what thing accepts the H? The SO4. You okay with that? So the conjugate base means which one accepts the H plus when I go that direction. You okay with that? Yeah. All right. The equilibrium constant or the gas phase reaction, that is 4.3 times 10 to the negative 3 at 300 Celsius. Yada yada. There's at equilibrium something. There's no options down here, right? Based on what I had just erased, it was asking whether you had more products or more reactants at equilibrium. So of this, tell your partner, are you going to have more products or more reactants? Okay. So which one do we have? Equilibrium is products over reactants, correct? How do I get a decimal in my answer? This number has to be bigger than that number, right? So the reactants were dominant at equilibrium. Thumbs up if you're okay with that idea. Okay. Next, the Shelley's principle is not on this one. Some of you still need to redo that, so maybe we should talk about it. At least I think some of you need to redo it. I know I should not, because some of you really suck and deserve it. That's boots though, brand new. No, can you? They're spotless. Okay, here we go. The Shelley's principle predicts that the moles of H2 in the reaction theta will increase. So tell your partner at least one way to make this go up. Tell them, ready, go. All right. So the easiest one would be to say add more what? NH3. Or a trickier one we could say increase pressure. Is that what you said? Decrease. Okay, good. That's the right answer. Decrease pressure. What's the third way? Remove N2. Good. That seems like it'd be backwards, but remember, if you take away, this fights that by making more over here. Someone said the word heat, but we don't know where the heat term is. It doesn't say it, right? It doesn't say whether this is endo or exothermic. All right. You may know that this is the way it's written is endothermic. because we've been dealing with the Haber process the whole time, but it was reversed. We were making NH3, this is a reverse. I like it, but see if you can do this. You may have to look at your notes.
It's like.
Page plus POH.
All right, we should definitely be done with this by now. So the way I would do it, and there's more than one way to do it. I would take the negative log of 1.94 times 10 to the negative 10. Did anyone do that? What did you get on the calculator, Wayne?
9.7.
9.7.
Yeah.
Okay, now that is the pH, correct? So now I just need to take 14 and subtract 9.7. 4.3 would be the post. Yep, pH plus POH is equal to 14. Okay, feel all right about that?
That means good.
This is an interesting question here. Without any options, it's really tricky. Consider the whatever, it cannot be established when blank is are placed in a 1 liter container. So it'd be something like A SO3 B O2 C SO2 D. And O2. What is it? It's a tricky question. In order for equilibrium to be established, we have to at least have this. That will break apart to take, or to make this, right? And we have to, at minimum, have both of the reactants. Okay, so I can put none of these in and just put this in, and it will be equilibrium. Clear that? But if I have none of this in, I have to have put both in. So it's kind of tricky. What it's trying to get you to demonstrate, is that equilibrium can be reached from just a product breaking apart back to this reactants. I have to look at exactly this, but if you just put SO2 in, it won't happen. If you just put in O2, it won't happen. But if you put SO3 in, it will happen. I'm not sure that that was perfect, but
Wait, so we can't remove this. What would this be?
it would be something like when SO2 and O2 are not, or something. Well, hold on. It would say something like only SO2, like A would say. It would be very specific. Probably by the end of this week, but, well, actually, that's a lie. Chapter 16 and 17 are combined into one test. So we're definitely done with 16, probably by the end of tomorrow. 17, we'll see. We have a random Thursday off. So, I don't know. We don't have another full week ever? Oh. Spring break's the week after. No, cares about what? According to Arrhenius' concept, an acid is a substance that donates a proton. It's a proton donor. Now, you weren't wrong, Seth, when you said H. That was correct to go to H plus. All right. How can we maximize the amount of this stuff? We know it's exothermic, so where would heat be written down? Come on, on the right. So the best way to make as much of this is to increase this, right? Decrease both of these. And what do we do with the temperature? Decrease the temperature. If it produces heat, it wants to be somewhere that's cold, so the heat can go somewhere. What about pressure? Would we do anything with pressure? Decrease the pressure, right? There is no Le Chatelier's principal question on this test. When I cut all these, I must have had 15 to 16 weeks. What does it mean? I heard it. It completely dissociates in water. If we only would have had this before the last test, huh? Yep, this was dead on there. And it was the most missed question. And there was the answer right there. Oh, a week late. Whatever, that's easy. Okay, so there was a ton of multiple choice there. I know the letters, the answers weren't there, but hopefully that would help. So today's the 21st. If you're going to study for the multiple choice section, you should probably rewatch March 21st video. All right, percent ionization. Like, what? This is forever ago. It's not. So percent ionization is equal to the concentration of H plus divided by the initial concentration of the acid times 100. It's different than Ka, but it's not really that. Whenever you find a percent, you've done it for your test, your whole life. You take what you got, divide it by the total, and multiply it by 100. Now, the reason it's in this chapter is that you can find percent concentration from the pH. All right, so it has this example, says the H plus is equal to this value, and the initial is that. So it literally is just 0.123, so I put the 42 over 0.1 times 100. That's all. Okay, so how do we do this with pH? So if I tell you that you have the pH of something is equal to 1.86 of a 0.05 molar C2H3O2 acid at a specific temperature. All right, and I want to know the percent ionization. It's not very hard. You need to know the concentration of H plus. Right? Because it's going to be H plus concentration divided by initial times 100. So if I have the pH, I should know how to find the H plus. So I take and raise it to the negative 1.86. And then I divide that answer by 0.05 and times it all by 100. When do you have it? 27.6. We would say it's 27.6% ion. That's a pretty big number. But does anyone know on the street how to know that it should be sort of a bigger number? The low pH, good job, Tim. A low pH means a lot of H plus. The higher the H plus, the higher the percent ionization. All right, you do this. Okay, this is the most important part of today, and that's calculating pH from Ka. We did 1,000,000 Ka from pH, correct? It's not that much fun. So we want, it says calculate the pH of a 0.3 molar solution of acetic acid at 25 degrees Celsius. Why is there a temperature?
Because it's temperature related, but that temperature doesn't actually matter.
There you go. All right, it doesn't matter for the math we're doing, but it matters in the universe. All right, now the problem is, it's weird when I import these slides. It gives you the Ka. In these problems, it will give you the Ka. It says the Ka for acetic acid is 1.8 times 10 to the negative 5. Okay, I want to know pH. In order to know pH, what do I need to know? I have to know the concentration of H plus. It's not too hard. Ka, I know, is equal to H plus, right, times A minus over the initial. Sound familiar? All right, let me put this in there. I know that 1.85 times 10 to the negative fifth is equal to, what do I know about these values right now?
That they're equal.
That they're equal to x squared over. We did them both ways already?
So do it again.
Yeah, it's fine. Over 0.3, right? Yeah, I don't know, we did. Okay, so now what is x equal again? H plus. Once I have H plus, I can do anything I want, right? As far as H is concerned. So I need to multiply both sides by 0.3. Then I need to take the square root of both sides. Do that. So you're going to have that answer what x is equal to. Get it back up on that number. Okay, good. Now what do you do with this number?
You say that's the log, yeah.
All right, you take the negative log of it. 2.6.
Oh, it's so cute.
Yes, the pH is equal to 2.6. The 0.3 was given in the problem. I just scrolled down too fast. So to solve for pH from Ka, you have the initial. It will give you the Ka and you just do alpha. And remember, this works because this number right here that we should technically subtract is really small. Like technically, we should do an ice table for all this and yada, yada, yada. But it really, since it's so small, we don't need to worry about this subtraction. But I think it says this on one of the slides. Okay, so all this was just the slides to set up what we just did. It says 2.64, so this isn't super accurate, but that's probably the calculation. Okay. Polyprotic acids are kind of hard. There's good news. Then we have to do the polyprotic part. Usually, I haven't ever seen it not be this way. If there's a question with the polyprotic acid, they only ask you for the first protonated hydrogen. So polyprotic acids have more than one acidic proton. So like H2SO4. They give off H plus twice. So they would have twice the effect on the concentration of H plus, right? Would mean they have twice the effect of or on the pH. So if the difference between the Ka for the first dissociation and subsequent Ka values is 10 to the third or more, that's the pH generally depends only on the first dissociation.
Wait, so can't we just do the thing where it's like add the thing to multiply and like raise the
Yeah, I'm lost. What this is saying, and it works almost every time, is if there's a large difference, then just do it off the first Ka value. So here we have ascorbic acid. That is vitamin C, in case anyone cares. So it has two H's. The first one is 8 times 10 to the negative fifth. That's its Ka. So what we're saying is H2C6H6O6 goes to H plus HC6H6O6 minus. This is the first ionization where the H plus was given on. Are you okay with that? Or dissociation, sorry, not ionization. And its Ka is 10 to the negative fifth. Well, the second one is now this. That's the second one, and it says it's 10 to the negative 12. Well, is there 1,000 difference here or 3 exponents different? Yeah, this one's tiny compared to that one, right? You with me on that? So what it's saying is that this one would be the one that really affects the pH more than the second one. So if we were going to do math, we would just use this Ka. It would be the 8 times 10 to the negative. Oops, sorry, then they're never going to make you combine. Like they will in college, and they're super, super tricky. But all we have to care about is if, and it always is, by the way, that I've ever seen, as long as they're at least 3 powers of 10 away from each other, then you just go with the first one. How do you feel about it? Raise your hands if you understand this. Okay, all right, that's half. So you'll be given both KAs, and you just need to check, are they 3 exponents away? Yes, they are. Here, no, they're not. So citric acid will be a lot harder to figure out. We won't do it on the test, I promise. Yes.
So on sulfuric acid, it just said large for the first
Yeah.
one.
It's like, it's a really strong acid, so it's basically,
Large. Large.
large. And if you care, which most of you won't, but sulfuric acid, the H, the HSO4 minus 1 is typically treated as a weak acid, even though H2SO4 was. Yeah. All right. Next up. You say my name? What?
Go back.
Sorry. Right here?
Yeah. Okay. Make sure he's got a pretty good start.
Who's ever heard of like the tartar sauce flavor, whatever? It's the bottom.
Wait, are you serious?
Oh, cute.
That's so creative. Sorry. Shut up. I can't even pronounce it.
All right, here we go.
Tartaric.
Let me just hold on. Oh, we're close, friends. We're on 97 out of 127. Oh, 130. I must have added a few. Let me. I'll come back, I promise.
Yep.
As your Spencer. Okay, here we go. Yeah, I look more like you probably. Still have your Oscar here. There we go. Okay, do you want to do this problem like we've done a ton of these? Okay, do it, 2 minutes.
It's been, all right. Oh, yes.
All right. Did I do it right? No, I only do that for percent concentration. Yeah, because it was Ka equals x squared over x is this value plus the time squared. Okay, what I get? 6 point what? Negative 6? There's a lot of sixes in there. We agree? Okay, no different. The Ka for formic acid is this. What's the pH of a 0.25 molar solution? Take a minute, see if you can get this one. You ready? What do you think? You think it's gonna look good? You think I overlap things, Daniela? You have no faith in me. Oh, I keep it. That's not bad. That is not bad.
That's
All right, here we go. So, yada, yada, yada. We have that equals x squared over 0.25. So I took 0.25. Oh, I screwed that up. I put a 0.4. Why? It's 0.25. Was the last one 0.4?
No, last one.
I don't know. I got 0.4 in my hand. Put 0.25. You okay with that? And I took the square root. I'm very proud of this square root signal because I made this one after I was already over here. I've never been more proud of myself in my entire life. Okay, I take the square root of that, it gives me an answer, and then I took the negative log of it, and my pH is equal to 2.02. All right, sounds good. Good. Okay. Good. All right. I'm so proud of that square root. All right, are we ready? We spent this entire chapter, 100 or like 90 slides on acids. Now we got 100 slides on bases. I know, I'm joking. It's the same math. It's the same. It's just for solving for not H plus, we're solving for OH minus. Yeah, we have the 4. Let's do a little bit. All right. Yeah, everything's pretty much the same. Here we go. That bases react with water to produce hydroxide. You heard that? Fastest. The equilibrium constant expression for this reaction is that instead. And guess what it simplifies to?
Wait, is it x squared over I?
It is x squared over I. But we got a giant star, asterisk or whatever right here. If we're doing it for bases, my x is equal to what? OH minus concentration. So my friends, the only thing that is different, and you're going to get it wrong, and I love you, and it's just the way life is. The only thing that's different is when you solve this math now, you're finding the POH. But the test never gives a crap about POH. It wants what? pH. So if you're ever doing a math problem with base, your final step is to always subtract whatever you just did from 14, and that's your real answer.
I was just gonna ask if like everybody misses this just because they forget to put an O.
No, they missed it because they forget that they're solving for POH. Because every single math step is the same.
So every single time we see it's a base, we should like put a star and like red flag.
Yeah, so this is what I would do. If I see it's a base on my paper, I'm going to do 14 minus, and then I'm going to do all my math right.
I think the 14 minus is
Bigger, my fault. I got this. 14 minus, and then I'm going to do all my math. The other only thing that's different is we don't solve for Ka. You would need to make sure it said Kb. It's the same math, but it's not for an acid, it's for a base. Now you're like, what kind of butt faces would care? Well, it's the AP graders. They're the ones that would test.
So then look at your work and then they use A, B instead of Ka.
Yeah, if they give you a base and you write out that Ka equals something, you're in trouble. Okay. Kb can be used to find hydroxide and through it pH. Because remember, if this is important stuff, if I know the hydroxide, I can take the negative log of the hydroxide concentration, and that will equal the POH. Right? So I wouldn't do it this way if I were you. I would say, what do I start with? 14 minus, and that equals my pH.
So
it never
exists solely for the reason to change it into pH.
Pretty much. And it's just because our world, we define things based on pH. So, I mean, we have both scales, but we'll just always report it with one of the two, but we can use the other one to find the other. Okay, sort of around that. Same rules apply here. Which one of these is the strongest base? It's the one with the smallest exponent, the smallest negative number. Oh, never mind. There's a 5. There's a 4 right here. It's my fault. All right. So it says, what is the pH of a 0.15 solution of NH3? All right. It tells you the KB is 1.8 times 10 to the negative 5. So, well, we can do this. All right. I have 14 minus all this math, right? So I know that, whoops, 1.85, sorry, oh my gosh. What's the Italian language? Okay, so I multiply both sides by 0.15. Square root it. And that will give me my x value. You don't have that number already?
0.0016.
0.0016. Now, is this what I subtract from 14? No, I take the negative log of this, and that equals
2.7.
2.7. 8.
2.784.
Okay.
3.
1. No.
Okay, it doesn't matter. So now I take 14 and subtract 2.78. And what do you get? Okay, now I got a question. Is that pH a base? 11 is greater than 7, right? Okay, so does that make sense then? Do we want this to be a base? Yes. You, if you forgot this part, you would be telling me that your pH of a base was 2.78. And your brain, which I know doesn't work on AP tests, but it should. Your brain should say, uh-oh, I did math and got an acidic pH for something they told me is a base. Oh, I forgot to subtract from 14. Don't forget to subtract from 14.
14.
Okay. Hey, look, we got the same answer last time. I gotta stop my recording a few minutes early. So for